Okay, let's get started talking about how to analyze a mixture of solutions. And the simplest case we're going to work on is a spectroscopic analysis of dyes. So let us imagine we're working with two different dyes. The first one will be acid red, and we've gone into the lab and we collected an absorbance spectrum for acid red at multiple concentrations. And because we have absorbances that are less than about 1 or 1.5, we can see if this follows a linear trend, if it follows the Beer-Lambert law. So recall, the Beer-Lambert law says that the absorbance at some wavelength should be proportional to the concentration. So to mathematically state that, absorbance is proportional to the concentration scaled by the path length, which for this case is just 1 centimeter, and the molar absorptivity at this particular wavelength. We've picked this wavelength because there's a large response of the dye in the absorbance at this wavelength. If we'd picked 700, we wouldn't see a large response. So let's pick a wavelength that has that large response to the dye concentration. So if I make a graph, I'll pick the absorbances at these wavelengths to plot on the y-axis here, and on the x-axis I've plotted the concentration. Now if I fit this data to a line, I'll get a line the slope of which should be the molar absorptivity times the path length. So since our path length was 1 centimeter, our molar absorptivity is just the slope of the line. So 0.0182 was the slope, and that's our molar absorptivity at this particular wavelength. Now if we add another dye solution into the mixture, let's look at how acid yellow responds to light. So if we just put acid yellow into a cuvette and measure its absorbance at these concentrations, we'll get a graph that looks like this. So pick what you think is a good wavelength for acid yellow. Hopefully you've picked something around the maxima here, which is 405 nanometers. So this should also obey Beer's law. We'll have absorbance for acid yellow in this case instead of acid red. It was proportional to the molar absorptivity of acid yellow times the path length, which is 1 centimeter, times the concentration. So we can make another graph that shows the absorbance on the y-axis and concentration on the x-axis, and once again the slope should just be the molar absorptivity times the path length. So from that we again get the molar absorptivity for this dye at this wavelength, acid yellow at 405. Now let us say we encounter a solution that's a mix of both acid yellow and acid red. And we can see a lot of acid yellow components over here and a big acid red peak over here, but if we look back at our graphs, acid yellow also absorbs a little bit at 405, and acid yellow doesn't absorb much at 514, but it might be absorbing a little bit. So when we look at the wavelength at 514 and the wavelength at 405, we'll get absorbances at these wavelengths, but these absorbances are actually a mixture. So at 514, we're actually seeing a mixture of the acid red at that wavelength. So that's the concentration of acid red scaled by its molar absorptivity, plus the concentration of acid yellow scaled by its molar absorptivity at this wavelength, at 514. How about the concentration here at 405 nanometers? The absorbance at 405 was 0.647, so that 0.647 is actually also going to be a sum of the acid red and the acid yellow, scaled by their different molar absorptivities at those wavelengths. So if we have any hope at all of trying to find the concentrations of acid yellow and acid red, we're going to need a little bit more information than what we have already. So what do we have? We know the molar absorptivity of acid red at this wavelength, and we know the molar absorptivity at acid yellow at 405, but what we don't know is the acid red molar absorptivity at 405 or the acid yellow at 514. So we're going to need to go back to our calibration data and get molar absorptivities for those. So if we go to 405 in the acid red plot, we'll see that there is a response at that wavelength to the concentration of the dye. So let's make another graph that shows the absorbance on y, the concentration on x, and here are the intensities, the absorbance values at 405. And you can see the slope here gives us the molar absorptivity, and it's much, much smaller than the slope would be here. It's much less responsive at this wavelength, but there still is some response that we must account for. Similarly, let's go to the acid yellow plot and look at the absorbance values at 514. It is very small, but we need to check and see if there really is a response. So let's use Beer's law again, plot absorbance at 514 and concentration, and we do see that the absorbance scale is very, very small. There's not much absorbance, but there still is some. So the slope of this line, which is a very, very small slope, accounts for the molar absorptivity of acid yellow at this wavelength. Okay, now we have enough information to go back to our mixture and try to figure out what the concentrations are of the two dyes in this mixture. We have a system now of two equations and two unknowns. If we'd had three unknowns, we would need to have measured a third wavelength. If we had four unknowns, we'd need to have measured a fourth, so that we get enough information to solve this problem. Now this problem can be solved pretty simply by algebraic rearrangements, but if we got more and more components, algebraic rearrangement would become very difficult. So an easier way to do it is to introduce a matrix way of solving this. So we create an absorbance matrix. This is just another expression of Beer's law. Absorbance is proportional to the molar absorptivity times the path length times the concentration of acid red and acid yellow. So we've just written Beer's law. We've pulled the molar absorptivity and the path length into a matrix called K. We'll just call it a K matrix, and that's our concentration matrix. So this is a 2x1 matrix for absorbance because we have two components. And this is a 2x2 matrix because we have those two components measured at two wavelengths. And then here's another 2x1 matrix for our concentration. So how can we solve this? Well, if we want to get concentration by itself, we would multiply both sides times the inverse of K. So if we had our absorbance matrix here that we've populated with our actual absorbance values, and our K matrix that we've populated with our molar absorptivity values, all we need to find is the two concentrations. And we do that by multiplying this matrix by its inverse. K inverse times K would just give us 1, basically, the identity matrix. And K inverse times A would give us the concentration because K inverse times K cancels. So we're now at a point where we're going to need to do a little bit of matrix algebra. And if you're good at doing this by hand, that's great, but there's an easy way to do this with Excel. So let me show you how to do this process in Excel. I've plotted our 2x1 absorbance matrix here. Here's our 2x2 K matrix here, and we need to find the inverse of this. So we'll tell Excel to please calculate the inverse of this matrix, and the inverse will have the same dimensions. So I've selected an output area with the same dimensions. And we're going to write a command that we want the matrix inverse, and then we have to tell it which matrix we want it to invert. So we select this matrix. Now this is an array calculation, so we can't just now press enter. We must press Control Shift and Enter to get our inverse matrix. So this is the inverse of our K matrix, our molar absorptivity matrix. Now if we go back to what we were trying to do, we're trying to multiply the inverse matrix, K inverse times A, so that we can solve for C. So let's ask Excel to do that math as well. The output, what will the output look like? Let's go back. The output will be a matrix with 2 rows and just 1 column. So let's select an output area with 2 rows and 1 column. And now we're going to tell Excel to multiply mmult, these two matrices. K inverse will be the first, and the absorbance matrix will be the second. And again, it's an array, so we'll press Control Shift and Enter to get our concentration. So this is the concentration of acid red, and it had micromolar units. Our molar absorptivity was inverse micromolar, inverse centimeters. And this was acid yellow, also with micromolar units. So now we've got our concentrations, and that's what we were after. Now, you might argue, and reasonably so, that while this matrix approach is a good one, we've also thrown out a tremendous amount of data. When we picked only 2 wavelengths to analyze, we threw out all the other wavelengths that we'd taken the time to measure. And that's actually a big compromise. We've compromised a lot for the simplicity of this approach. So there's actually a way you can continue to solve this problem that uses both of these wavelengths plus all the others that we've actually measured. And that will require us to make a big spreadsheet. So let's go back to Excel, and I'll show you a spreadsheet that contains all the acid red spectra that we've acquired, all the acid yellow spectra that we've acquired. So what are these spectra? These are lists of wavelengths that we measured and the absorbance that we measured at each individual concentration. So here's the lowest acid yellow concentration, here's the next highest, and the next highest, and so on. And then we also have a column that has our mixture, the wavelength and absorbance of the mixture, and here's to remind you what that mixture looked like. So if we're going to use the complete spectrum, we're going to need to calculate the molar absorptivity, not just at 2 wavelengths, but at all of them. And that might sound truly awful to do, but it's not too bad in Excel. So if we want to get the molar absorptivity of acid red, what we would do is we would take the absorbance of acid red at the lowest concentration and at 1 wavelength, and we would divide it just by its concentration. So in this case it was 29 micromolar. And that would give us the molar absorptivity based on this measurement. Now we actually tried to measure the molar absorptivity at multiple concentrations, and it would be better to include all of those in an average molar absorptivity. So let's actually calculate an average. So let's add to this the absorbance of acid red at that same wavelength, but at a different concentration. So I'm going to divide by the next concentration, which was 32 micromolar. And to get an average, I add all of these together. This is 39.7. And the last one is the absorbance at 800 for 45 micromolar. And to get an average, of course, you sum everything together and divide by the total number of measurements, and we measured 4 times. So this tells us that our molar absorptivity at this wavelength is more or less completely negligible. So if we want to do that for every wavelength, we can just copy and paste this down. Now there's 2 quick ways to do this. One is to put the crosshatch mark over the lower right-hand corner and start dragging it, and it'll calculate that same formula repeatedly. Or you can just double-click on that crosshatch and it will populate the rest of the cells. So what we have now is a molar absorptivity for acid red at every single wavelength. So let's make a graph of that and see how it looks. Okay, so we're going to insert a chart, an XY scatter plot. And I haven't selected the data yet, so I need to tell it what data I want. So I'm going to right-click and select data. I'm going to add a series, and the X values I want are wavelength values. So I'm going to click on this, and to select everything in the column, you can press Control-Shift down, and it will get that whole wavelength column for you. And then my Y values I want are the molar absorptivity values. So again, I'll do Control-Shift, hold those down while I press the down key, which didn't work, so we'll try it again. That worked. And we should have a nice molar absorptivity plot. So this is acid red. Okay, I don't want dots, I want lines connecting them. So let's do this. Change chart type. We want a nice smooth scatter plot. Alright, oh that's better. So that's the molar absorptivity data for acid red. And it looks just like the spectrum does, doesn't it? Okay, we're going to do the same thing for acid yellow. We're going to calculate the molar absorptivity at every single wavelength for acid yellow. So we'll do an average. This absorbance divided by its concentration, plus the next measurement we made, the absorbance divided by its concentration. And again, 25 was the concentration for that one. This one divided by 31, plus this one divided by 38. And again, we need, because it's an average, to divide by the total number of measurements, which in this case was 5. And here's our acid yellow molar absorptivity. Okay, let's make a graph just like that one, but for acid yellow. So I'll copy and paste this one. I don't want the acid red data, I want the acid yellow data. So we'll drag it over. Let's add a chart title just to make sure that we know which one is which. We want a chart title. Okay. Alright, so now we've gotten to a point where we have molar absorptivity at every wavelength for both dyes. And our mixture, remember, is a sum of the concentration of acid yellow times this spectrum, plus the concentration of acid red times this one. So what we're going to do is we're going to take our guessed wavelength, for our mixture, and try to make a model mixture based on these other two that we have, based on the other two spectra that we have. So we're going to make a guess about what the concentration of this is and what the concentration of acid red is, so that we can make a guess at what we think they are. So let's guess 10 micromolar for both, just as a starting place. So my guessed concentration of acid red in this mixture is 10, this is 10, not based on anything logical except for the magnitudes of the calibration curve, the data that we have. So our mixture spectrum should be the concentration of acid red times the molar absorptivity of acid red, which we calculated over here, plus the concentration of acid yellow times the molar absorptivity of acid yellow, which is right here. I'm going to put that part in parentheses. And so at this wavelength, 800, we've used the molar absorptivities at 800 as well. Now I'm going to do the same thing at the next wavelength that we've used, 794. But before I can drag it down, I have to fix the references to the cell for the concentrations of these species. And the way you fix references is by putting a little $sign in front of the number in the reference, so that when I drag this down, this calculation still references the right concentration cells, AA1 and AA2, which are here, but by dragging down and copying to the next row, I've now copied down the molar absorptivity of U7 and I7. So these concentration values are fixed. Alright, I can copy this down to get the next ones, and so on. And we can get a spectrum based on our guess of these concentrations. So let's add that spectrum to our mixture. Let's add some data. So this is our guess. The x values are the wavelengths. The y values are the absorbance. And we've added this to our graph. So the blue is the mixture that we measured, and the orange is the one that we guessed. Now our guess was not that good. We guessed pretty far off. This spectrum, our guess, does not match the real spectrum. So what we could do is just changing the numbers. Looks like we need to go up a little bit for both. And we can just keep playing with those numbers till we get closer. Now, what's a way we can tell if we're getting closer? One way to tell is to calculate the difference between this graph and this one. And those are called residuals when we do that. So let's calculate the residuals between our guess and the mixture. And residuals are usually more helpful if they're squared, because that will make them always positive. And we'll get a residual for every single wavelength. So the residual here will be very large, the residuals over here will be very small. So the best part of the residuals that would help us would be to sum them all together. So that's what I'm going to do. I'm going to sum the residuals together. And that number, the sum of the residuals, should get smaller as these two graphs get closer together. So I'm going to start playing with these and see if we get smaller. Right now our residuals is 1.65. By changing the numbers a little bit, we got a smaller residual, and that's what we wanted, and the graphs got closer together. So let's make another wild guess. Oh, my guess was too big. We got worse in this area, lower in this area, and our residuals didn't get much better. So you can sit here and play with this for a really long time if you want to, and get your number closer and closer together. But as you might expect, there's a trick in Excel for actually doing this for you. We can ask Excel to keep changing these two numbers, these concentration guesses, until we hit the smallest possible residual. And the tool for doing that is called Solver. So if we click the Data tab, and if you have Solver added in, and I will show you how to add it in if you do not, the Data tab may have Solver already. If it doesn't, just be patient and I'll show you how to add it. We'll click Solver, and Solver will say, what do you want to minimize? And we'll say we want to minimize the residual sum of squares. So that's what the cell we want to change. We're going to minimize it, not maximize it, by changing the two concentration cells, these two cells. So A1 and A2, we want it to change those. Now we could add constraints if we want to. What are some reasonable constraints? We could say they can't have negative concentrations, or we could say they can't be bigger than some number, but for now let's just let it go and make as many guesses as it wants to try to find the right concentration. So let's click Solve. And let's keep the Solver solution just to see what it came up with. And it came up with, look, the blue and the orange curve are completely overlaid. And it came up with a guess for concentrations of 36 micromolar for acid red and 26 micromolar for acid yellow. So using the whole spectrum, it was able to get a concentration for both acid red and acid yellow. So using Solver, we got a little bit better numbers. And that's maybe a more tedious way to do it, but a more accurate way as well. Alright, I said I would show you how to put Solver into Excel if you don't have it already. To do that, you have to add it. So go up to your File tab, and what you do is you click Options, and tell Excel that you want to include add-ins, and tell it you want the Analysis Tool Pack and the Solver add-in, and click Go. And it will say, do you really want the Analysis Tool Pack and the Solver add-in? If these boxes aren't checked, then check them, and then you will click OK. I already have them, so I'm not going to click OK, I'm going to click Cancel. And good luck trying this on your own. It's a powerful tool, so I hope you will use it.